Okay, so in this video, we're going to look at mass spectrum as well as IR spectroscopy, okay? So let's start with some basics of mass spectroscopy. When it comes down to it, really, there's some patterns that I want you to recognize. And those patterns are going to exist for halogens, specific halogens. We're just talking about chlorine and bromine, like you see here. We're also going to look for things like methyl groups that can come off, as well as any types of major groups. Like in this case, we've got benzene in both of these. So keep in mind what's happening with the mass spectrum. And in this case, these are electron ion spray. So what we're doing here is we're bombarding a molecule with electrons and watching how it falls apart. Now, the parent ion is one of the things that you need to pay attention to. The parent ion is like, where are these things coming from? What's the overall mass? So that's the mass of the spectra. And so this we refer to as the parent ion a lot of times. Okay, so basically that is how much mass does your compound have? But before I go into that too much, or because there's really no need to, right? Because all you're doing is calculating the mass of the compound. I want you to look at this more closely. Right here, we have a split. Right there, we have a split. And what that is indicative to me immediately is chlorine. And the reason why is because chlorine has two major isotopes. One is 35 and one is 37. And it is 75%, give or take, 35, and about 25%, 37. Well, we see that pattern here. And you can check and look. That is going to be 35 difference and 37 difference between those two. The other thing that I notice here is that I've got a peak right around 78. Well, 78 happens to be the mass of that benzene. So those are things that we can look at from this and go, I recognize that. And those are the patterns that I want you to be able to see. Similarly, bromine has two isotopes. One is 79 and one is 81. And they're about 50-50. Sorry about that, I'm writing 5 instead of 50. So 50-50 on the spectrum. So see how we've got that split right here. And if you look at the mass difference, that's what you're going to find between those two. Again, we have about a peak of 78 or so, and that is your benzene. Okay, on to the next ones. Okay, here are the other things that I want you to be able to see. And I've given you two examples for a reason. We have here cyclohexane, but this is methyl cyclohexane. And to the right, we have ethyl cyclohexane. Okay, what's the difference? Well, I see the difference pretty quickly. And that is this difference in this last peak. In addition to what is the overall mass, right? Like here we have a mass that's a little bit lower than this one. That makes sense. Well, the gap here you'll find is about 15 versus the gap here you'll find is about 29. That is the difference between a methyl group and an ethyl group. Okay? Other types of splits that you see with mass spectra, we could get into way more detail than this, but I'm not really looking for that most of the time. You will see that this is about 15 in between most of these, right? And we see the same pattern over here. And that's because what's happening is you're losing one carbon at a time. And so that's sort of what we see. But I'm not that concerned past that level about mass spectrum. So let's start looking into infrared spectrum. Okay. In this infrared spectrum, we see this structure. And in infrared spectrum, what we're looking for is what are the functional groups. That's all we're looking for. We're not looking for, what is the exact structure of this. Most of the time we can't see that. But what we can see is what type of functional groups do we have. Now, please know with mass spectrum, IR, NMR, I will give you a chart to read so that you can see where local peaks should be. Now, I'm going to go from what's in my head on this video, but you can reference some spectra chart, okay? What I notice immediately about this spectra is right here. And that is a peak around 1750. What that tells me is that I've got this C-double-O bond. The other thing that I notice is that whenever I have a C-double-O bond, I check, do I also have an OH? If I were to have an OH, there is usually a broad type of area over here. That I do not see. So what this tells me is that most likely I have just this guy, or if I've got another oxygen that needs to be put in place, then probably we're going to have some type of ester. Okay. So here are some examples that are further examples of these types of things. On the left, we have 2-butanone. So again, we're going to have a C-double-O peak around 1750. To show you what I mean by that broad peak, in butanoic acid, we have a C-double-O peak, but we also have this big broad one over here. That's what an OH peak looks like. Now, this one even has a little bit more definition than what I'm used to seeing. So this must be a really, really nice IR. Usually I see maybe one and then maybe some peaks over here. So don't be confused at the exact shape of that. It may have to do with the ability of that particular IR. Okay, the other thing that we can see here, and keep in mind there's lots of functional groups, so these are just examples of what those functional groups are. The other thing I forgot to say earlier that I should note, anything that's above 1500 we're looking at. Anything below 1500 is considered the fingerprint region. So like right here over, we don't really look at that too much unless that's what your specialty is. If that's the case, then great, but we're not really going to look at that in more detail. I want to show you the difference between single bonds, a compound with a double bond, and a compound with a triple bond. So first we have hexane right here on the top left. Now this is, again, it's a really intense IR. I'm not used to seeing them quite this intense myself. So this is going down even beyond where it appears that the spectrum goes, which of course is not even possible, but it seems to happen. So what this is just showing is that we've got peaks right below 3,000, and that's about it. We see other stuff in the fingerprint region, but that's about it. Look what happens as we introduce, though, a CC double bond. We see here that, sorry about that, this is the CH that is coming away from the rest of those CHs. That is the CH from the CH sp2 carbons right there, okay? Okay, so it's not just one CH, it's the CH2, and it's the hydrogen right up here. And you're not going to necessarily see a difference. Sometimes you do. It depends on the compound. It depends on the IR. But we see some splitting that's happening there. Then when we have the triple bond, we notice some other things. See how this is fully broken apart now from that 3,000 peak, or the number that's a little bit above, or below 3,000. So we've fully moved away from that 3,000 peak, and we see a much more defined hydrogen. Now, one thing to keep in mind here is that when we have a CC triple bond, there's only one hydrogen there. So that's all we're looking at. So really and truly, that's a pretty decent size peak for just one CH stretch there. Sometimes with carbon-carbon double bonds or triple bonds, we also find peaks in other locations that you should pay attention to. But I don't see an extreme peak example of that in these instances. I hope that helps you look at these MS and IR spectra so that you can sort of see what's going on in those molecules. Next, we move on to H&MR.